Hi everyone, in this video, I'm going to go over how to answer the pre-lab question number 2 to 5. Number 2, 3, and 4, this is going to be how to calculate pH of the strong and weak acid that is going to be covered in lecture chapter section 14.6 to 14.7. And then when we look at the basicity or acidity of salt, this is going to cover in lecture chapter 14.8. Okay, so I'm just going to give you the overview of this. So let's take a look at question 2. Okay, so question 2 asks us to calculate the theoretical value of pH of hydrochloric acid. Okay, so note that before you can calculate the pH, you need to know first whether the acid is a strong acid or weak acid, because we are going to treat this differently. If the given acid is a strong acid, okay, so if it's strong acid, you are going to follow the instruction from lecture chapter 14.6. If the acid is a weak acid, then you are going to follow the instruction from the lecture 14.7. Okay, so what do I mean by that? Okay, so let's take a look at this one. Okay, so hydrochloric acid. Okay, so if you think about hydrochloric acid, this is one of the 6 strong acids. So that means I'm going to follow the procedure or instruction from the chapter 14.6. Set up an equation first. Okay, so in this case, we are going to react hydrochloric acid with water, and that is going to yield hydrogen ion and chloride ion. Now, the next thing that you can see from this equation is that the hydrochloric acid and proton is 1-to-1. The reason why it's 1-to-1, because this is a strong acid. When you have 1 mole of HCl, it's going to also produce 1 mole of hydrogen ion as well, right? So that's why it's 1-to-1. So that means the concentration of hydrochloric acid and the hydrogen ion or proton in this case would be the same. So just a reminder, okay, so proton can be used interchangeable with hydrogen ion. Okay, so this one is without water, this one is actually include water. So again, the reason why the concentration of hydrochloric acid is the same as the proton in this case, or this one right here, is because this is a strong acid, it's completely dissociated. Okay, so that means if you have 0.01 molar of hydrochloric acid, you are going to end up observing the same molar for hydrogen ion as well. This concentration of hydrogen ion can be used to calculate for the pH. Okay, so the pH can be calculated from the negative log of the concentration of the proton or the hydrogen ion. In this case, we know the concentration of hydrogen ion, so all you have to do is just plug it in. So the pH of this solution would be negative log of the concentration, which is 0.01 molar. Okay, so if you calculate for this, it's going to come out to be 2.0. Okay, so in terms of the decimal place, okay, so there is the rule of the decimal in logarithm. Okay, so the number of sig fig that present before you taking log, okay, so the number of sig fig in the concentration here, so this is 1 sig fig, is going to translate into the number of decimal place in your final answer of the pH. So therefore, that's why your final answer contains only 1 decimal place, okay, because of that. The pH of 2, which is lower than 7, is indicate that this solution is an acidic solution. So question number 3 give us the weak acid, acetic acid. And it wants to know that if you have the same concentration of acetic acid, would it yield the same pH, less or more than the concentration of hydrochloric acid, right? So you probably notice that this is 0.1 molar of strong acid, okay? This one is 0.1 molar, right, of the weak acid, okay? So that's the weak acid. So that means we are going to treat these two differently, because the one is strong acid is going to completely dissociate, right? And then weak acid would be only partially dissociated. So I'm going to use the full arrowhead here, okay? So it's not reversible, okay? So now what you are going to take a look at next is I'm going to do the same thing that we did in the previous problem, which means that I'm going to looking at this in terms of molarity. Okay, so if we have 0.1 mole per liter of hydrochloric acid is strong acid, so therefore you are going to end up with the same concentration for hydrogen ion as well. Okay, so because we know the concentration of hydrogen ion, therefore the pH of this solution can be calculated from using the negative log of that concentration of hydrogen ion, right? So pretty much this one right here, plug it in the negative log, right? So if you do this, you are going to get 1 pH of 1. Okay, so that means this solution will have pH of 1. Again, the reason why it's not the same as the previous one, because these two problems, right? So problem number 2 and number 3, they have different concentration of hydrochloric acid. Okay, so that means the pH going to be affected by the concentration of the acid as well. So now let's take a look at weak acid. Okay, so weak acid in this case is acetic acid. So if I write this more correctly, I'm going to replace this HA to an actual acetic acid. Okay, so it's going to be HCH3COO. Okay, so as this acid give up its proton, is going to become its conjugate base, which is CH3COO minus. Okay, so if you want to write this more correctly, it would be that. Okay, so the HA is just a generic. Okay, so what does it mean then? Well, it means that if you have 0.1 molar of acetic acid, you are going to have less than 0.1 molar of hydronium ion because it dissociates less than 100%, right? So which means that if you take negative log of this concentration that have less than 0.1, you are going to get a greater number than 1 molar. So therefore, in this case, you are going to see that this solution would be less acidic. So therefore, the pH would come out to be greater than 1. Okay, so again, the reason for that, because the available proton is actually less than the initial concentration of the acid. Okay, so therefore, the pH will come out to be greater than 1 because it's less acidic. For number 4, we see that this problem involved with the weak acid. Okay, so it's also involved with the acid ionization constant and also pH as well. Whenever that you see weak acid, pH or Ka, this one you are going to follow the procedure that we cover in chapter 14.7. Okay, so chapter 14.7 will cover weak acid. Note that this question is similar to calculation number 1 that you are going to do in lab. Okay, so in order to find out the Ka, we are going to set up an equation. So first, we are going to react weak acid with water. I'm going to use the reversible arrow because this is a weak acid, right? It's happened at equilibrium. So acid is going to donate proton to water. So therefore, you are going to get hydronium ion and its conjugate base. Okay, so the next thing we're going to take a look at is because we want to find out the equilibrium constant or the acid ionization constant, which is at equilibrium. So in this case, we need to find out the concentration at equilibrium. Okay, so what I'm going to do is that I'm going to set up the expression first. Ka expression for this would include product divided by reactant. So if I do this, it would be the product of those two products, right, multiplied by each other and then divide by the reactant, which is that. Okay, so we are going to exclude water again because water is liquid. Okay, so now how can we plug each of these in? Okay, so we know the concentration of weak acid already because given is 0.1. What we don't know is the concentration of the hydronium ion and its conjugate base. Okay, so what you can do is that I'm going to recall 122, which is the RICE table, so that way you understand this better. Okay, so I'm going to use RICE stand for reaction, right? So this is the chemical reaction. I is the initial, C is the change, and E is the equilibrium concentration. All of these are going to be expressed in terms of concentration, which is molar, okay, mole per liter. Okay, so what I can do is that I'm going to exclude water first because water is liquid, right? So we're going to exclude that. Okay, so the initial concentration of HA is 0.1. Okay, so at the beginning, before the reaction starts, you are going to see that the concentration of hydronium ion and its conjugate base would be 0 because nothing happened yet, right? So before you react water with weak acid, nothing happens. So therefore your product would be 0. Now, what would be the change? Well, the change in this case, I'm going to give it equal to negative X. Same thing with those two. Okay, so except it would be positive because over time, HA would decrease by X mole. We don't know how much, right? So that's why I said X mole. And over time, the concentration of hydronium ion or proton and its conjugate base will increase by X time, right? So I don't know, again, what is X, right? We're going to figure it out. Okay, so at the end, at the equilibrium, what is going to happen is that you are going to add the initial and change together. So you are going to get 0.1 minus X. And for those two, you can add these two together. So it's going to be X and X. So this X here is going to represent the concentration of hydronium ion at equilibrium. Same thing for this X as well. And this concentration of hydronium ion at equilibrium can be found from the pH value. You probably notice that the pH of this equilibrium is already given, which is 2.53. So therefore, in this case, what I can do is that I can find out the concentration of hydronium ion by doing the anti-log, right, of the pH, which is 10 raised to negative pH. If I do this, I'm just going to add, I'm going to replace this pH with 2.53. Okay, so get that number. You're going to get 0.0029512 molar. Okay, so I'm not going to write yet. Okay, so what I can do next is that, remember, this is represent as X, right? Because that's concentration at equilibrium. So this is a concentration at equilibrium from the pH. So this is going to be X. So if this is X, the concentration of the conjugate base also going to be another X as well, right? So that means in this case, the conjugate base would be the same concentration as the hydronium ion. Now, what about the concentration of this acid at equilibrium? Then, well, all you have to do is what? Subtract the initial, right, by the X value, and that's what you're going to get, right? You probably notice that it's very, very close to 0.1. The reason for that is because this is a weak acid. It doesn't dissociate much. So that's why you probably notice that your initial concentration of HA would come out to be very close to the initial concentration anyways, right? Because it doesn't undergo change by much at all. So if you plug off this N back to the Ka expression, you are going to get 8.97 times 10 to negative 5. So in terms of sig fig, you probably notice that the concentration has 2 sig figs. So therefore, 2 sig fig would limit your final answer. So I'm not going to route yet. Okay, so that's why I underline, right? So you can just leave it like that with the underline, or you can route up. If you route up, it would be 9.0, okay, times 10 to negative 5. You probably notice that the Ka value come out to be a very small value. So this indicate that this acid is a weak acid, right? Because it doesn't want to go in the forward direction at all. So at equilibrium, you have more of the reactant than the product. That's what it means. For pre-lab question number 5, this is going to be involved with lecture chapter 14.8. Okay, so this is going to be the pH of salt solution. Okay, so we are going to looking at this for salt right here and determine whether it's going to be pH neutral salt, acidic salt, or basic salt. Okay, so some of this salt, note that it can be used in agriculture as the pH adjuster, right? So if you want to lower pH of soil or increase pH of soil, right? So some of these salt can be used for that purpose. Okay, so let's take a look at how can we do this. Okay, so before I get into the analysis of this, I want to also mention that this analysis also going to be similar to the chemical equation that you need to answer for the pre-lab. Okay. So let's take a look at first sodium chloride. Okay, so whenever that you see ionic compound are going to refer as salt because they contain metal and non-metal. Okay, so in this case, this is a salt, sodium chloride. Okay, so this salt comes from the neutralization reaction between the acid and base. Okay, so the hydrolysis of this salt will tell us whether it's going to react with water or not. Okay, so hydrolysis means you are going to break this apart in water. So if I do this, right, so if I dissolve solid sodium chloride in water, this is what you're going to get, right? You are going to separate them into cation and anion, sodium and chloride. Each of these ions, we are going to react them with water to see what they will produce. Okay, so first I'm going to react sodium with water. Sodium is plus water. If you think about water in terms of ionization, right? So this one, you are going to end up having proton and hydroxide, right? Because proton and hydroxide add together is actually going to pretty much form water as well. So in this case, you probably notice that if you have a positive sodium, it's not going to react with a positive proton, right? Because they have the same charge, they repel. So that means the only thing that sodium is going to react would be the hydroxide part of the water. So that means in this case, if I react this, you are going to get sodium hydroxide, okay? And the other species that we have left would be proton that come from water. Now, if you're looking at the list of the strong base, you probably notice that sodium hydroxide is one of the strong base. Okay, so what does it mean by the definition of strong base? Strong base means that when you dissolve strong base in water, they will not stay as molecule. They are going to completely dissociate. So that means in an actual reaction or solution, these molecule right here would not stay as sodium hydroxide, but it's actually going to separate into sodium and hydroxide, which means that this one will actually most likely to go this way. It's not actually going to use strong base. So that means this reaction right here will not take place. So that means when sodium react with water, it will not react at all. That's what it means, because it's unlikely to produce the strong base, because strong base completely dissociate. Right? So that means this one produce no product. Therefore, there is no reaction between sodium and water. So the conclusion of the sodium is that it does not react with water. So therefore, sodium ion is a pH neutral ion. Okay, so the next one is we are going to react the chloride ion with water. So it's going to be the same analysis as the previous step, right? So that means in this case, if you're looking at water, you can separate this into proton and hydroxide ion, right? So if you're looking at this, chloride has a negative ion. Therefore, the only thing that it's going to attract to is going to be this positive proton, right? So therefore, the final product of this would be HCl and OH minus. Note that if you're looking at the identity of hydrochloric acid, this is a strong acid. So again, strong acid is unlikely to stay as a molecule like this. So therefore, is most likely to actually go in the reverse process, right? Because completely dissociated, it doesn't want to stay as a molecule. It's most likely want to stay as a chloride and proton. So therefore, in this case, it's making these ions to cause no reaction with water. So therefore, chloride ion does not react with water. So in this case, chloride ion is pH neutral. Any ion that after you write out the equation with water, if it yields a strong acid or strong base, just note that that ion would not react with water. So pH of that ion would be pH neutral. Okay, so in this case, because both of them yielding pH neutral, therefore this salt is considered to be a pH neutral salt. Now let's take a look at ammonium chloride. Okay, so first step, again, this is salt. Again, how do you know it's salt? Well, it's contained cation and anion, right? So ammonium is the cation, is the one of the polyatomic cation, right? And then we have chloride. So in this case, first step, what you need to do is to separate them first, because we need to use each of those ions to react with water at the end. Okay, so hydrolysis step would be you are going to break apart ammonium chloride into ammonium ion and chloride ion. And the next step is we are going to write out acid or base ionization in water, which means you are going to pretty much bring these or each of these ions to react with water. So let's start with the first one, which is ammonium ion. So now what would be the product of this process then, right? So in this case, you're going to do the same thing. We know that water would give off either proton or hydroxide ion. And clearly in this case, you probably notice that the ammonium ion is positive. So therefore, it's going to interact or react with hydroxide. Okay, so it's going to react with the opposite charge. So therefore, the answer or the product of this would be NH4OH plus H plus. Okay, so if you look up the list of strong base, so ammonium hydroxide is not part of the strong base. So therefore, this reaction will happen, okay, because for the weak base, right, the majority of the compound will stay as a molecule. So that means it can yield this molecule. Okay, so that means this can happen. Note that this reaction, when ammonium ion react with water, is actually produce H plus. What does it mean? Remember the Arrhenius definition. Arrhenius definition state that the acid is going to produce proton in water, right? So in this case, this proton right here is the acidic identity. So therefore, this ammonium ion, because it produces proton in water, ammonium ion is an acidic ion. Okay, so again, I'm not going to worry about this ammonium hydroxide, okay, because this is going to stay as a whole molecule, okay, because a weak base. Okay, now what about chloride? Well, we already did this chloride in the previous example, right? So chloride does not react with water, so therefore chloride would be pH neutral. So one is pH acidic, the other one is pH neutral. You probably notice that the ammonium is going to raise the concentration of proton in water, causing this reaction when this salt dissolves in the water to be an acidic solution, right? So therefore, the ammonium chloride is an acidic salt. Next, calcium carbonate. Okay, so calcium carbonate, you are going to do the same thing again. Okay, so you are going to separate them into cation and anion. So we are going to get calcium and carbonate. Okay, so the next thing we're going to take a look at is we are going to use each of these ions to react with water. Okay, so I'm going to react the calcium ion with water. Okay, so note that I'm going to use 2 water. The reason for that is because this charge of calcium is 2 plus. So if you think about each water contains 1 proton and 1 hydroxide, since this is 2 plus, so you need pretty much 2 hydroxide, right, to actually balance the charge, right? So in this case, you are going to end up producing calcium hydroxide, right? So 2 hydroxide from there. And then the other species that we did not use would be the proton. Okay, so note that again, calcium hydroxide, you look up the list of strong base, right? So this one is one of the strong base. So therefore, in this case, it will not yield a molecule of strong base because strong base want to dissociate, right? So it doesn't want to stay as a molecule like this. So it want to actually stay as calcium ion and hydroxide ion. Okay, so that means this reaction right here will not occur. Okay, so there is no reaction, no product will form. Okay, so again, to summarize this, calcium ion does not react with water. So therefore, calcium ion is pH neutral. What about second one? Okay, so we have carbonate as well. You're going to do the same thing. You are going to react carbonate with water. So again, if I write this out in terms of each component in water, it would be proton and hydroxide, right? So this is a negative charge. So therefore, it's going to attract to proton. So in this case, you are going to end up having HCO3 minus plus OH. Okay, so this bicarbonate ion is not part of the strong acid or strong base. So therefore, it is going to stay as a molecule. So therefore, this reaction will happen because this molecule will stay as it is, right, after these two react with each other. So note that after carbonate react with water, is actually produce hydroxide ion. Okay, so again, according to the Arrhenius definition that we learned earlier, is that base, right, is going to produce hydroxide in water. So therefore, in this case, this is going to tell you about the base identity. So that means that when carbonate ion react with water, is produce hydroxide ions. So therefore, carbonate ion is a basic ion. Okay, so note that calcium is pH neutral, carbonate is basic ion. Because carbonate will produce a lot of hydroxide ion in water, so it's going to cause the concentration of hydroxide ion to increase, making the solution to be a basic solution or alkali solution. So in this case, the calcium carbonate would be a basic salt. Okay, so calcium carbonate is part of the limestone, right, that used in agriculture to pretty much increase the pH of the soil, right? So it's just because calcium carbonate is the basic salt. All right, next one. Okay, so we're gonna take a look at aluminum sulfate. Okay, so aluminum sulfate also used as the pH adjuster in soil as well. Okay, so let's take a look at whether it's going to use in lowering pH or increasing the pH. Okay, so let's take a look at this. Okay, so first step, again, this is salt, is contain metal and non-metal. So I'm going to have to separate them, right, or hydrolyze them in water. So this one is going to separate into 2 aluminum ion and 3 sulfate ion. Okay, so again, this subscript tell us that there are 2 aluminum, right? So this tell us that there would be 3 sulfate. Okay, so the charge of aluminum can be found on the periodic table, right, the location on periodic table, and then sulfate is part of the polyatomic ions you need to learn from last term that contain 2 negative charge. Okay, so again, do the same thing again. We are going to react each of these with water. So I'm going to start with aluminum. Okay, so aluminum ion add to water. So again, the part that is going to react with water would be OH, right? So it's going to produce aluminum hydroxide, and the other one would be proton. So again, because this is 3 plus, so therefore you are going to end up needing 3 water in this case. Okay, so you need 3 water. Next, what we're going to take a look at is we need to look at the list of strong base, right? So aluminum is not one of them. So therefore, the molecule of aluminum hydroxide will stay as it is. So therefore, in this case, when aluminum react with water, it will yield aluminum hydroxide because this is not a strong base. When aluminum react with water, it actually yield proton as well. So therefore, in this case, this proton right here tell us about the acid identity. So therefore, aluminum ion is an acidic ion. So now if you're looking at the reaction between sulfate and water, so again, the sulfate would be the one that is going to react with proton in water, so to form monohydrogen sulfate, and the other species would be the hydroxide ion. So in this case, you probably notice that this is not one of the strong acid or strong base. So therefore, this reaction will take place. And if this reaction take place, then you probably notice that the OH tell us about the base identity. So therefore, we can say that sulfate ion is a basic ion. You probably notice that, hey, Ami, this is acidic ion, this is a basic ion. Would it make the overall salt to be neutral or acidic or basic? This is depend on the Ka and Kb value. Okay, so let's take a look at the Ka and Kb value. Okay, so Ka value of aluminum ion tell us that this reaction right here, right, once is produce H plus, right? This is the value of it. Okay, so 10 to negative 5. Now the Kb tell us that if sulfate react with water, this is how much hydroxide ion would be produced. If you're looking at the equilibrium constant for these two, you probably recognize that equilibrium constant of aluminum ion is actually greater than the sulfate ion, which indicate that at equilibrium, you are actually having more of the proton than of the hydroxide ion, right? Because this one, it doesn't want to go forward at all, right? So these two products would be a lot smaller than these two products, according to the Ka and Kb value here, right? The relative Ka and Kb value. So therefore, in this case, because the reaction will produce more of the proton because of a higher value of the equilibrium constant of aluminum ions, so therefore it's making this salt to be an overall acidic salt. So that means if you want to lower the pH of your soil, this is what you are going to have to go by with aluminum sulfate. So this section is going to help you answer the chemical equation for acid and base. For hydrochloric acid, pretty much what we see earlier, right, is going to react with water, and the arrow that we are going to use would be the one-head arrow. Okay, so it's indicate that this is a strong acid. For acetic acid, you are going to use the reversible arrow because this is a weak acid, right? So it's similar to what we see as well. And for the base, you are going to pretty much break apart the OH, right, to indicate that this compound will yield OH or hydroxide ion. Same thing for ammonium hydroxide as well. You are going to pretty much separate the hydroxide from the cation. Note that the difference between strong versus weak would be the arrow type that we use. Now for the chemical equation for salt, okay, so this is similar to what we see earlier as well. For sodium chloride, you first will need to separate them, right, or dissociate them. This is what we call hydrolysis. And then you are going to react each of these ion to water, and it's turned out that there is no reaction for both sodium ion and chloride ion. For ammonium chloride, do the same thing as well, right? So you are going to pretty much separate them into cation and anion, and then react each of these ion with water in the acid and base ionization. Okay, so in this case, you probably notice that as I mentioned, right, so there would be the reaction between ammonium ion and water, and there is no reaction for chloride ion. And because ammonium ion produce H+, so therefore this salt is an acidic salt. Now, next one for calcium carbonate, right? So you're going to do the same thing. So you are going to break apart the calcium and carbonate and then react each of these with water, right? So calcium will not react with water, so therefore there's no product. Okay, so go back to the previous explanation, okay, for this. And then for carbonate, okay, so this one is going to react with water. So as this reaction happens, you probably notice that it's formed hydroxide ion, which indicate that this salt is a basic salt. Okay, last one is aluminum sulfate. So this one, again, do the hydrolysis first and then react each of those with water. So we note that both aluminum and sulfate will react with water. Okay, aluminum would yield acidic proton, and sulfate would yield hydroxide, the basic hydroxide. So these two are producing both hydroxide and proton. How do we know whether this salt is acidic or basic? Then you are going to look at the relative Ka and Kb. So you're going to compare the Ka and Kb. And it's turned out that the Ka of aluminum ion is actually greater than the Kb of the sulfate ion. So making this salt to be an acidic salt. All right, that's it for this lecture video. Okay, so pretty much we cover pre-lab question 2 to 5. And the last part of the video, I actually covered the chemical equation as well. So I went over how to write acid-base ionization for hydrochloric acid, acetic acid, sodium hydroxide, and ammonium hydroxide. And then this last part of the chemical equation, we look at how to write out the hydrolysis equation for this salt, and also write out the acid-base ionization equation as well.